Hello, so we are going to start off with the equation for chemical potential. This equation states that chemical potential of component I is equal to the chemical potential of component I at a standard state plus the gas constant times temperature multiplied by the natural log of the activity coefficient of component I times the mole fraction of component I. Next, taking equation 1-30 is provided in the textbook, which states that the driving force is equal to the mole fraction of component I over the gas constant times temperature times the derivative with respect to x sub j times the chemical potential of component I. Here I'm going to plug in the equation for chemical potential into the equation 1-30. And that will look like this. The driving force is equal to the mole fraction of component I over the gas constant times temperature times the derivative with respect to x sub j of the chemical potential of component I at a standard state plus the gas constant times temperature times the natural log of the activity coefficient of component I times the mole fraction of component I. From here, I'm going to cross out factors that cancel. So that is these two gas constant times temperatures. And then additionally, when we take the derivative of the the chemical potential at a standard state, that is a constant, so the derivative of it is 0, so I'm going to go ahead and cross that out now. So just cleaning that equation up, I'm left with this. Next, I'm going to perform the chain rule and get the derivative of this natural log with respect to x sub j. So that means the driving force is equal to mole fraction of component I times the derivative of the natural log, so it's going to be 1 over what is inside the parentheses, multiplied by the derivative with respect to x sub j of the inside of the parentheses, according to the chain rule. Again, crossing out any factors that cancel. Next, I'm going to take the derivative of this inside expression, so what was inside the parentheses, again, crossing out any factors that cancel after in addition to multiplying this out across, these two will cancel. And this expression can actually be rewritten as the derivative with respect to x sub j of the natural log of the activity coefficient of component I. So then rewriting this using this little reduction, we are left with this expression. We can rewrite this expression and expand it out. Specifically, this, what is in the parentheses here, can be expanded out quite a bit. For my example, I'm going to have my j be 3, so I'm going to have 3 terms. I'm going to go ahead and write that out. we can then summarize this very long equation in this matrix that I've already previously written out. Wrote it out on a separate sheet of paper. Here you can see that when you do a standard matrix vector multiplication, taking this top row by this column, you get the equation we solved for before. You can see we've got our xi, we've got our partial derivative of the natural log of the activity coefficient of I. In this case it is 1 because it is in the first column, and over our the partial derivative of the mole fraction of x sub 1 times our derivative of x sub 1 over our dx sub j. In this case it is 1 because it is the first. Note the diagonal 1 plus in front of our expression can be expressed by the Kronecker delta, which states that when I equals j, the Kronecker delta equals 1, but when j does not equal I, the Kronecker delta equals 0. So in this case, this is j equals 1 because it is the first column and it is the first row, so I also equals 1. So for this specific term, I equals j, so our Kronecker delta equals 1, so that's why we have the 1 plus. But for here, our j equals 2 because it is in the second column, our I equals 1 because it is still in the first row. I does not equal j, so we do not have the plus 1 term. This matrix and this formula can then be summed up again, this time using equation 1-32 as provided in the textbook, which states that the thermodynamic factor matrix sub ij, so gamma ij, is equal to the Kronecker delta plus the mole fraction of component I times the partial derivative of the natural log of the activity coefficient of I over the partial derivative of x sub j at standard temperature, pressure, and taking the sum. So that is how you get from equation 1-30, as we started off the problem, to 1-32.